Hello, welcome to a mini lecture on application of the differential equations that we've been studying. This application is spring problems that arise in physics where we have a spring hanging from some rigid support and we want to be interested in measuring the motion. It turns out that the motion is governed by a second order linear homogeneous differential equation that we've been studying. And so we'll look at two different situations where on the left here we have x double prime plus some constant times x being equal to 0. That'll be one particular setup. And then after that we'll look at adding in another term, this one being x prime. And so then it's still second order, still linear, and still homogeneous. And so, but it deals with a different situation physically behind the scenes. And so let's develop the two methods and not go into the solving of the equations. Let's focus more on where the equations come from and what the solutions look like. So we'll call it spring/mass systems. And at first what we're going to be looking at is called free and undamped motion. We'll explain those two words in a second. So I have this spring that's attached to some rigid support and it naturally hangs there unstretched, a distance capital L. Okay, and then what we're going to do, so there's an attached end to the rigid support and there's the free end. So to the free end we're going to attach a mass, and that naturally then will stretch the spring, and we're going to call that distance that the spring gets stretched just by hanging the mass S. So it's elongated, a distance S. And it all depends on the mass. Next up, we have Hooke's law, which says that the spring will exert a restoring force, called capital F, we'll call it here, that is opposite to the direction of elongation. At the same time, it is proportional to the amount of elongation. When we say that two things are, or one thing is proportional to another, what we say is, for instance, A is proportional to B means that A is equal to some constant K times B. And so if F is proportional to Ks, F is proportional to S, then we say that F is equal to Ks. And K is just the constant of proportionality. And it has to do with the spring's properties. Now there's a weight that needs to be balanced by the restoring force. These two things should be equal to each other. mg, the weight, mass times gravitational constant g, should be equal to that restoring force, Ks. And so what's going to happen is we could also start out by extending or displacing the mass even further away from its natural hanging position of L plus S. What we can do is stretch the spring so that we have a distance x that you displace it from equilibrium. So then what changes is that K, the spring constant K, isn't multiplied by S anymore for the restoring force. Now it has to be multiplied by both X and S, the sum of that, Kx plus S. Kx and then plus Ks if you want to distribute. Okay, but we have to take into account direction. When the force is acting upward, we're going to say that's negative, and when the force is when it's downward, that's going to be positive. Okay, just by convention. And so then the sum of these forces should be equal to the mass times acceleration. So the restoring force is negative because it's acting upward. The weight is positive, it's acting downward. So minus K times the quantity of X and S added together should then be added to mg for the total forces acting on the spring. Newton's second law says that, well, as long as you have free motion where there's nothing that's going to dampen the motion, theoretically then it can continue forever. And so the mass times the acceleration should be equal to the sum of these forces, and from above we have the fact that mg is equal to Ks, and so you can subtract that over. And so if we were to distribute this, we have mg, and then we have minus ks. Well, from above, that's just going to be 0. And so then those two will basically balance each other, cancel each other out, and then we'll just have the negative k times x. And so that's what the mass times the second derivative should be equal to. And this is our first look at the differential equation. It's not in our standard form, but it's going to be how we derive it from first principles. Okay, so here's a look at the motion, where we have the equation set equal with the constant in front of the second derivative divided through. Still it's homogeneous, and there is no x prime term. Here's an example of such a solution. Once you go and solve that, the solution is going to be oscillating. It's going to be, here's an example, 1/4 the cosine of 4 root 6t. Okay. Those are the kind of functions that have their second derivative equal to some constant times themselves. And so, sines and cosines. And so, this is actual visual of the motion. And since down is positive and up is negative, then we actually, when we go to graph that curve, it'll be the reverse of that. And so it'll have an amplitude, which you can calculate. And this one, it's 1/4. It'll have a period, which you can calculate based off of the original period of cosine divided by this multiplier on t. Frequency, we can do 1 over the period, and all these things we can, if we were to want to go further with this, we can look into. I just want you to understand like where the equations come from and what types of solutions, what they look like, and why they are that. Okay. So next we'll then throw in another term. We're going to look at a different situation physically, still about a spring, still about being suspended, but now we're going to add in another force, and that force is going to be something that will dampen the motion. Theoretically, this motion will continue forever. There's nothing to stop it. It's free and undamped. But in our next, we'll consider what happens when we are damped. A dampening can actually be done with hanging the spring in some kind of medium, water, and still doing the same kind of motion where you extend it, and then the motion eventually will be dampened. It will then eventually head to 0. You know, there will be we'll be able to get to equilibrium and stay there. And so this other drawing at the bottom, this other graph here at the bottom is what's called a dash pot. So it can be some physical, actual machine sort of that will dampen the motion mechanically. And so then the equation has an extra component to it regarding the first derivative, and then there's some constant of proportionality involving that. It will be negative, acting in the upward direction. Once again, this is still behind the scenes, you know, Newton's law, m times a, right? Mass times acceleration. And now the sum of the forces will be the minus kx, and now minus beta times x prime. Okay, what's this beta about? It's about the constant of proportionality for the damping force. This damping force is proportional to the instantaneous velocity, and it's negative since this force acts in the direction that's opposite of the motion. And so now we have still second order, still constant coefficients, and if we move the terms around, we're still homogeneous. And we've seen how to solve these based on the roots of the auxiliary equation. We could have 3 different, very different looking solutions, and that's what we'll look at on the next slide. Just what the solutions look like and why would they look like that. And so let's say your roots are real and distinct. For example, you solve the auxiliary and you get -2 plus or minus root 5. Okay, we've seen then what we're doing here is assuming that the solution is e to the rx. So these are my r's, plus -2 plus the root 5 and -2 minus the root 5. And we could factor out the e to the -2. And this would be a look at what that solution would be like. Okay, now the graph of it would be that the exponential term on the outside will will then cause the motion to be what's called overdamped. The motion basically will be dampened too much, where it ends up getting to equilibrium rather quickly when you have real distinct roots to your auxiliary equation. That's called being overdamped. Now, the second part would be then, what if you have a double root, where a repeated root would be a better way to say it. When that's called critically damped. And so you'd have e to the negative 4t, and then remember how we have to multiply by t on the second solution to be a linearly independent solution to the first one. And so then if we factor out again the exponential term, what we'll be looking at then is damping, but not to the point where it kills the motion dramatically fast like the other one. And so we have a linear term. So this is like a double exponential for the real distinct roots. This is just like an exponential and then a linear term. So it's going to go to zero eventually. It's just going to do it in a slower way. You're actually going to get some motion. You're going to go down to your minimum, and then eventually you're going to go back up and just end up at equilibrium there. Okay? And the third most interesting type is when you have, you guessed it, complex roots. And so with complex roots, for instance, -2 plus or minus 4i, notice that every time I'm doing my real part, it's a negative. That's that's going to end up being why the motion ends up going to zero. If that was positive, it would end up growing exponentially instead of decaying exponentially. And so the solution would look like that. We have sines and cosines, so we have oscillations. Oh, it's going to be damped. I mean, there's an exponential term on the outside. It's going to be damped, but we call it underdamped, where you're actually going to get some oscillations. You're going to bounce back and forth around equilibrium. The graph would look something like this, where you either these graphs, they start from 1, 0, or -1. Doesn't really matter, but I just want you to see a visual. And these might not even, I don't even think these are actually the graphs of the functions that I have there, but this is what they generally look like though. Okay, and here's an actual graph, I believe, of where I pick a C1 and C2 from the previous solution, and it's just a blow up of that graph where we have the oscillations, and then eventually we get to equilibrium. And so that's it. It's just a little mini lesson just to go through an application of what we've been doing for differential equations, and it's hopefully you understood, and if not, shoot me an email and I can explain it. The notes will be posted on our website. All right, thank you.